Okay, so I made a couple of Canvas announcements regarding your last 3 module exams. I'm going to just condense them into one remaining module exam that will be administered the last Wednesday of the semester. So that will be with basically material from modules 5 and 6. I had 2 module 6 exams before because I was envisioning separating them on carbohydrates versus amino acid stuff, which is based on kind of the pool of questions from prior years. It's going to be pretty hard to make 2 exams for that module because really it's not a whole lot of chemistry with the biomolecule stuff. It's more of like structure related, and there's only so many questions that I can ask. So the last exam, I'm just calling it module 5, but it's going to be on stuff from 6 as well. That's going to be 60 points. The 2 exams that were removed, those 120 points have been removed from the grading scheme. So the letter grade thresholds have been lowered accordingly, and that was updated in the syllabus. And I will post an updated version of the Excel file that you can put your points in and track your scores from that. So this module 5 is dealing with the alpha carbon. And so we're going to learn basically the formation of carbon-carbon bonds. And there'll be a little bit of a connection to biochemistry and how nature does this. And then that's our transition into the module 6. So the big picture of this, as I said, is chemistry at the alpha carbon. And let's just start over to the left of this slide. We have this carbon backbone with a carbonyl group attached to some X group. In the table, it defines what that X is. So if it's H, then it's an aldehyde, and then that carbon's at oxidation state 2. So carbon gives you the ketone, OH acid, O carbon is ester, and then N is the amide. So again, if you have a heteroatom, that's when you go up in oxidation state. That's what we just learned in the prior module. But the connection between all of those is really the alpha carbon. And we discussed a little bit before, the ketone is the only one that has 2 alpha carbons. So we'll spend some time on that. What are the issues with ketones in this chemistry? But for the most part, we're looking at the acidity of the CH bond at that alpha carbon. As we move away, we just label the carbons using the Greek alphabet, so beta, gamma, so on and so forth. Most of the chemistry that we see is going to take place at the alpha carbon. There'll be some offshoots of that we'll have to keep track of, but understanding what we learned about resonance will come into play quite a bit as we move through this module. So for this specific model, we have a methylene group. So that's a CH2 group. And the pKa, of that alpha carbon CH can be between 20 to 25 based on what the X group is. But it's significantly more acidic than a normal CH bond of an alkane. So say we have some base, and I'll just show a neutral base here, a lone pair. it's going to abstract a hydrogen. And when it does that, the electrons in the CH bond go on the alpha carbon. And so that is getting us up into what is drawn as the top structure there. So we have the lone pair on the alpha. The carbon is now negative. Then we have a resonance arrow where those electrons can be delocalized up onto the oxygen. So in doing that, it forms a carbon-carbon bond, and then we break that CO pi bond, and that becomes a sigma bond. And now that's negatively charged on oxygen. That reactive intermediate is called an enolate. So of the two resonance hybrids, the enolate is probably bears more weight in terms of where the negative charge is because oxygen's electronegative. But in terms of reactivity, the reactivity is primarily happening at the alpha carbon. And since it's a lone pair, carbon's negative, it's a nucleophile. It's supplying electrons in the mechanism. We know that nucleophiles react with electrophiles. And so over the course of these couple lectures, we're going to look at the different electrophiles and categorize them based on the oxidation state. So the number in red here is the oxidation state of that carbon. So X is going to be a leaving group. So mechanistically, the alkylation set of reactions proceeds through an SN2 reaction. You have a nucleophile, electrophile, it's just an SN2 displacement. And what are we doing here? Let me put some dots in. I'll say that alpha carbon's the red dot. The carbon of the electrophile bearing the leaving group is the blue dot. Regardless of what type of electrophile is employed, we're always making a carbon-carbon bond between the alpha carbon and then a new beta prime. I call that beta prime because starting from alpha, we're branching off into a different carbon chain. So the substrate already had a beta carbon, now it's branched, so that's beta prime. So all of these reactions will make a carbon-carbon bond. What differentiates the classes is the oxidation state of the electrophile you start with, and then what you end up with at that beta prime. It's always a reduction that's happening. So whatever oxidation state the electrophile is, in the product, it goes down by 1. So when I look at that, there's no heteroatoms, it's 0. I can tell that it came from an alkylation. If the electrophile is at oxidation state 2, that can be an aldehyde or a ketone. I've just shown an aldehyde. This is now a nucleophilic addition. So we've seen that before, like when a Grignard reagent adds to a carbonyl to make an alcohol. So here's the red. Here's the blue. Notice it's oxidation state 2, and then in the product it's at 1. So we've made the carbon-carbon bond. The beta prime carbon is at oxidation state 1, so it's an alcohol. And I can say because that is an alcohol, I know that we had to use an aldehyde or a ketone as the electrophile. The last electrophile is oxidation state 3. So those are the functional groups we just talked about. And so this does a nucleophilic acyl substitution. So let me highlight, see this group in blue? That group gets substituted for everything else that was in the enolate. Using the colored dots, that blue carbon ends up there. And there was our red alpha carbon. So because beta prime is now at oxidation state 2, by necessity it has to be now a ketone, because you have carbon and carbon. That tells me this came from a Claisen. So that's the overall reactions that we're going to study. We're going to get into the different nuances of generating the enolate, and then what are the offshoots of each of these. So alkylation, aldol, and Claisen, and then there's some variations of each of these that we'll study in terms of the nature of the nucleophile and the nature of the electrophile. So the take-home message for this is the alpha carbon is what generates an enolate. The oxidation state of the beta prime carbon in the product tells us how that carbon-carbon bond was made, meaning what was the electrophile used. So I've expanded out the OS2 and OS3 functional groups. So here we have an aldehyde. Here we have a ketone, then ester, amide, and carboxylic acid. The ketone was the only one with 2 alpha carbons. All of the other ones, since there's only 1 alpha carbon, it's really narrowing your choice about how you generate the enolate. In the ketone, I've shown alpha and alpha prime, meaning that they're different. And therefore, this ketone is not symmetric. If the ketone was symmetric, something like this, propanone, those 2 alpha carbons are equivalent. And so in that scenario, it doesn't matter which one you generate the enolate from. So the reason that, again, we're primarily focused on the alpha carbon was due to that increased acidity of the CH bond, because the reactive intermediate has that enolate resonance form which stabilizes the negative charge. This chemistry does not apply to the beta, gamma, or moving further out the chain. So when you look at these structures, your eyeball should go to the alpha carbon immediately. So what is responsible for that increased acidity? given that the alpha carbon is sp3 hybridized. So as we see with your normal sp3 hybridized carbon in green, we have an H attached to it. The pKa is 50, meaning that's a weak acid. So the fact that the carbonyl is next door enhances the acidity quite a bit. sp2 hybridized carbons, they're still weak, but not as much. And then sp are the most acidic or the less weak of that type of CH bond. And the reason the acidity trend runs that way is based on the percent S character. And that's just by taking the number of s orbitals, 1, divided by the total number of orbitals. So 1s plus 3 of the p's, that's the 4. Because an s orbital is spherical, it's closer to the nucleus, and that stabilizes the negative charge that's generated. So the carbonyl is special in that sense. It enhances the acidity of an sp3 CH bond. One of the complicating factors about generating an enolate, and again, depending upon what X is, so no matter what that is, you can draw at least 3 minimum resonance forms. If it's a ketone, there's going to be more. So if we, again, show the base deprotonating the alpha carbon, that generates that carbanion. We delocalize the lone pair onto oxygen. It's generating enolates, but look at the nomenclature difference between them. This one says Z, this one says E. The reason they're different is because now we formed a double bond, and we can think of that as an alkene, and then we can assign priority of the substituents of the alkene. So Z means cis or same, and the way that we know that it's Z, so the 2 red dots are the carbons of the alkene. You look at what is bonded to each, and then you assign priority based on atomic number. So if X was hydrogen, we would say oxygen would take priority 1, hydrogen priority 2 based on atomic number. On the other side, we have carbon and hydrogen. Carbon gets priority 1, hydrogen priority 2. They're on the same side, so that's Z, cis, or the same. And then the same logic applies for the E-enolate resonance hybrid. And you'll notice the oxygen is now on the opposite side of that existing carbon chain. So enolates because it ends in ATE, are negatively charged. The neutral version of that is called an enol. That just means the oxygen has an H. So enol is a combination of alkene and alcohol. So you have an alkene and then an alcohol. So primarily you find enols under acidic medium, but by and large, a lot of this chemistry is run with the negatively charged enolate. Any questions? So why does this get its own module, its own chapter? Why is it complicated? There's a lot of factors that go into forming the enol or enolate, and then again, the nature of the electrophile that you're using. And then as we proceed through this, we're going to encounter a stereochemical issue as well. So regarding the substrate that's going to form the enol or enolate, is it aldehyde or ketone? Is it a carboxylic acid derivative? For ketones, do you have alpha versus alpha prime? How many hydrogens does each have? What is the nature of the base that you're using? Is it a strong base, a weak base? How does that affect the equilibrium when you're generating the enolate? Is it enol or enolate, Z or E, geometrical isomers, and then what oxidation state of the electrophile is being used? So let's look at the most complicated example, a ketone that's not symmetric, because then we'll kind of know everything we have to contend with. How many alpha carbons are in this molecule? So we have 2. Once we locate the carbonyl, any carbon bonded to that is an alpha carbon. So the ketone is the only one that's going to have 2. So are the alpha carbons equivalent? So we have a CH3 that's methyl, then a CH2 that's methylene. So they're not equivalent. So what is the ratio? So methyl is 3, methylene is 2. So there's a statistical ratio. And then what complicates this is what base we use. How is the base matched to the different alpha carbons, and ultimately the stability of the enolate? Because remember, an enolate is an alkene, and alkenes have their own stability trend. So we end up with 3-2. So let's consider each alpha carbon separately. This one called alpha is a methyl group. It has 3 hydrogens. I'll show one of them and do the deprotonation. So we have alpha carbon H. Sodium ethoxide is the base, so the base is going to abstract that hydrogen. Notice this alkene. The terminal carbon has 2 hydrogens. So this cannot form E or Z. That's the only enolate that can be generated from alpha. So alpha prime, on the other hand, has 2 hydrogens. When we talk about unique sets in terms of proton NMR and that sort of stuff, we would say those 2 hydrogens are equivalent. However, under these conditions, I've drawn one as the wedge, one as the dash. These hydrogens are actually prochiral. That means that the carbon itself is not a stereocenter. But if we replace one of these hydrogens with something else, it becomes a stereocenter. So the reason that 2 different enolates are generated is when you deprotonate either one of these, it's primarily going to lead to one or the other, the E or the Z. So let's just show, the acid-base reaction. That carbanion will have resonance. And so that would be the Z enolate. If we deprotonate the other one, we would form the E enolate. So ultimately, from the methyl alpha carbon, that forms 1 enolate. The alpha prime can form 2. So with this base, sodium ethoxide, we would form 3 enolates. So that's summarized here. When we look at the enolate generated from the methyl group, let's just count. All of these structures are going to be alkenes with O and then the metal. So we'll kind of ignore that in terms of when we count. So let's just count how many carbon substituents are bonded to the alkene itself. This just has 1. the other two enolates have 2 carbon substituents. So that makes the alkene more substituted. So alkene substitution pattern. Then I have these other terms down here, kinetic and thermodynamic. Remember when we said that ratio of 3 to 2? A kinetic enolate, kinetic is rate. In terms of the statistics, 3 to 2, the base sees the 3 more often than the 2. Kinetic enolate is always the lesser substituted one. Thermodynamic, again, relates to the increasing number of carbon substituents on the alkene, so it's more substituted. A thermodynamic enolate will always arise from an alpha carbon with the lower number of hydrogens. So our base is sodium ethoxide. Our solvent is ethanol. So if we say that as a pK of around 16, the ketone pKa is about 20. So it's not a terribly large difference in magnitude between pKa's. So that's why we've drawn this arrow here, this equilibrium arrow. Chemically, what does this mean? So if we take ethanol, just straight ethanol out of the bottle, you add in sodium metal, it's going to evolve H2 gas to form your base. The base will then do its thing with the ketone to generate these enolates, but the pKa difference does not shove everything over here. That means you have ketone, base, solvent, and 3 enolates present in the reaction. For any reaction, you don't really want that, because when you put in the electrophile, it can react here, it can react there, it can react there. Maybe it does something with the base. Maybe it does something with the starting carbonyl group. So the acidity of the alpha carbon CH matters in terms of what base we select, because we don't want these enolates having the chance to go back to this through equilibrium. We want a strong enough base so that the pKa difference favors generation of the enolate only. So the base itself is no longer present, the starting carbonyl is no longer present. The nomenclature part, E versus Z. Again, you identify the 2 carbon atoms of the alkene. You assign priority. And again, that's based on atomic number. And then if priority groups 1 are on the same side of the pi bond, that's Z or cis. If they're opposite, it's E or trans. So why is that important? We're going from an sp3 hybridized carbon to sp2. The action is taking place at that sp2 hybridized carbon that was formerly the alpha carbon. Remember that a pi bond consists of, that hamburger bun looking electron cloud on top and bottom. That means the way you're looking at this, there's a pi cloud towards you and a pi cloud behind the projector. So when it reacts with an electrophile, the electrophile can come this way or this way. And as I said, in the product, you're regenerating an sp3 hybridized carbon, which will become a stereocenter. So those prochiral hydrogens, one is substituted for the electrophile. And the complicating factor of the enolates is there's 2 faces of that pi system, that double bond. So as we progress through this, we'll start looking at ways in which we can reduce the product manifold, how many things are formed by biasing the system somehow. So one of the things we can do to help ourselves get the best chemical yield, the best product we're after, is by starting with a base that has a great enough pKa difference that we're only forming enolates. We're completely consuming the carbonyl starting material. So another base that we learned about was sodium hydride. So for example, if that deprotonates from the methyl group, we have H abstracting H. The conjugate acid of that is H2, which is lost as a gas. So it's no longer in solution. The reason the arrow is drawn this one way is because now the pKa of H2 is about 45, and we were starting with about 20. So 45 minus 20 is a 10 to the 25 difference in pKa values. So delta pKa. But we're still left with this issue is that that base is not discriminating between the 2 alpha carbons. So we need to think of other bases, other ways of biasing the starting material. But by appropriately, looking at the pKa table, we can affect the equilibrium of the acid-base reaction. So again, the kinetic enolate comes from the alpha carbon that has the most hydrogens. because that generates the least substituted enolate. Another thing we'll see later on, the nature of the metal that's used for the base also plays a role. So now we're kind of drilling down into everything that's in that reaction flask is playing a part in the outcome of the reaction. So thermodynamic enolates, again, come from the alpha carbon with fewer hydrogens because we end up with a more substituted double bond. And then we have this issue of Z versus E. So say we're under acidic conditions or neutral conditions. I said the reactive intermediate was called an enol, so that's an alkene plus alcohol. The starting material, kind of regardless, is referred to as a keto form. So what's happening in terms of like acid-base chemistry here, say you have just hydronium. We can't form negative oxygen. So the first thing we do is activate the carbonyl. So we protonate it. Then we can have water act as the base. And so that now generates the enol. But that still suffers the same issue of, these three reactive intermediates here. You have the kinetic enol, the thermodynamic enols, and then the E and Z isomers. And again, the equilibrium of this, whether it favors the enols or the keto form, is based on the acid you used. But in general, a carbonyl group is preferred just due to bond strength. So a CO bond versus a CC double bond. So how do we know that this stuff is occurring, that it's actually happening? We can run these experiments with deuterium labeled, sodium hydroxide deuterium labeled water. So D2O is called heavy water. That's going to help us understand why stuff only happens at alpha carbons. And then in this particular case, I said these two hydrogen atoms at alpha prime were prochiral, meaning that if you substitute one of them, you're going to generate a stereocenter. So let's run through some of these scenarios to help understand how enolates are generated, and then also what is the effect on stereochemistry. So first question, what's the molecular formula of cyclopentanone? So we have C5H2468, and then oxygen. And then just for practice, let's calculate the molecular weight of that. So 12 times 5 gives us what? 60. 1 times 8 is 8. 16 times 1, 16. So what do we get here? 76 plus 8. Is that 84? So we're going to run the reaction with NaOD and D2O, and the action is only happening at the alpha carbons. So if every CH bond is substituted for deuterium, how does the molecular formula change? What do you think the answer will be? So in this case, since it's symmetric, the alpha carbons are equivalent. So there's a mirror plane. And the action's only taking place at the alpha carbons. Each carbon in the ring, besides the carbonyl, has 2 hydrogens, so there's 4 total alpha hydrogens. So our H8 gets reduced to H4, and then we've incorporated 4 deuteriums, and the oxygen remains the same. That happens because the beta CH bonds are not acidic. We're basically labeling each alpha carbon with deuteriums. So really we've increased the mass by 4 in this case, so we end up with 88 grams per mole. So we get B And then we end up with this thing, which is an isomer. It's called an isotopomer, just because we've swapped out hydrogens for a heavier isotope deuterium. And the reason that's useful is if you go into biochemistry and you're learning about metabolism, we've specifically labeled just the alpha carbons here, right? So if this were a probe for a metabolic process and we wanted to find out where on this carbon backbone is a reaction or a substitution happening, since the alpha carbons are labeled with deuterium, you would know if one of them was replaced versus if something at one of the beta carbons was replaced, because then the masses would change differently. And so these sort of labeling experiments with deuterium or with carbon-13 in terms of the carbon chain were really used in a lot of the classical research on metabolism in organisms. So to review from last module, so we have this ketone and we want to treat it with MCPBA. Do you remember what MCPBA with a ketone will do? So it's going to do a Baeyer-Villiger reaction where the oxygen of the MCPBA so that oxygen is going to insert between a carbonyl carbon and an alpha carbon. So we go from a ketone to an ester. In this case, since it's cyclic, the ring's going to expand. We go from a 5 to a 6. And so the answer for this would be B, because that's the ester. Both C and D are wrong because the oxygen's in the wrong place. And then A was basically our starting material. So why is that useful? From the symmetric ketone that we started with, alpha is equal to alpha, beta is equal to beta. Since we inserted that oxygen, we've now differentiated all of the carbons on that backbone. They're all different now. So that former alpha carbon has now been demoted to the delta position. And we said that acidity is only based on the alpha carbon. So we started with 2, we did the Baeyer-Villiger, now we have 1. And then we've moved those labels to a position where they're no longer acidic. So alpha CH bonds will undergo deuterium exchange. And now the next concept we're going to look at is if we have a starting material with an existing stereocenter and we treat it with a base to form an enolate, but we don't add any other electrophile the enolate is just going to get reprotonated. What happens to the stereochemistry? So in the example shown, this ketone, notice there's two different alpha carbons. So the alpha one in the ring has no hydrogens. Alpha prime has one hydrogen. The stereochemistry is set as S. So that carbon has 4 unique substituents. We can assign the S stereochemistry to it. Under equilibration conditions, so a weak base, a polar protic solvent, what happens to that stereo center? We run the reaction. Do we still pull out the pure S isomer? Has it converted to the pure R? Is it a 1-to-1 mixture, or is it some other ratio? So the answer for this is B, and let's understand why that is. The pure S enantiomer is going to form a racemic mixture of R and S. So we know that the carbon's sp3 hybridized. Has 4 sigma bonds. The substituents are all different, so that's the S center. We have our base, sodium ethoxide. It's going to deprotonate the only CH bond at the alpha position. So there's the carbanion resonance form. The hybrid is our enolate. So notice now this carbon is sp2 hybridized. It no longer has any sort of stereochemical information. Under these conditions, since it's in equilibrium, the reactive intermediate is just going to get protonated again from the solvent that's present, the ethanol. So let me redraw this, where we're going to put our eyeball like in the plane and sort of look at the edge of the double bond. It's a very crappy looking benzene. So we've put our eye here. We have the phenyl ring and the methyl group coming out towards us. The O- and the ethyl group going away. So now we're looking more flat. That pi bond system, as I said, has a top face and a bottom face. So when this collapses back down, and reacts with the alcohol, it's just going to get reprotonated. So I think based on how I'm looking at that, that would form the S enantiomer. If the protonation takes place from the bottom face, that would form the R. Because that carbon is sp2 hybridized, it's no longer chiral. The protonation takes place equally from the top and the bottom, so you get a 1-to-1 mixture of those enantiomers. And then that would be proven through polarimetry using a specific rotation measurement. It would be 0. Any questions before we move on? So the result, even though we're starting with something with a set stereochemistry of S, the enolate is achiral. It's protonated from either the top or the bottom face. So in terms of, this would be A is the response. There's nothing that's going to discriminate the face of that alkene to select out protonation one way or the other, so you get both equally. And really the key thing is that the enolate there is achiral. So we want to look at, these factors that are affecting the equilibrium and designing a reaction that's going to give the best outcome. So we've seen 2 bases so far. Sodium ethoxide in ethanol generally leads to an equilibrium. The sodium hydride in THF will force things towards the enolate. The issue with sodium hydride, it is a solid. So it has limited solubility in organic solvents, meaning that the reaction just to generate the enolate is probably going to take a little bit, and you'll have to monitor the time for that conversion. A soluble organic base that is strong is called LDA, or lithium diisopropyl amide. And it is generated from diisopropylamine, so a secondary amine. So there's only one NH. It's a pretty weak acid, diisopropylamine. So we have to use a very strong base to deprotonate it. That's N-butyl lithium. So N-butyl lithium is a carbanion. So it deprotonates that. The conjugate acid is butane, so its pK is 50. So 50 versus 40, that's a big enough difference to force this to form LDA. And the LDA is what we're using now as the base to generate our enolate. So we're going to think of that as lithium plus, nitrogen minus. The reason that this amine was chosen, these isopropyl groups are pretty big. So the nitrogen really can only function as a base. Even though it's negatively charged, it's not a good nucleophile, meaning it's not going to undergo like SN2 type reactions. It's just going to be a base to abstract hydrogens. So LDA we're going to use with our carbonyl compound to generate an enolate. So let's look at the difference between these bases. In terms of the hydrogen count for this model ketone in the middle here, it's not symmetric, so we end up with alpha and alpha prime. Alpha has 2 hydrogens, alpha prime has 1. If we take our ketone with sodium hydride and THF at room temperature, that's going to select for the thermodynamic enolate. So remember, that's coming from the alpha carbon with the least number of hydrogens. It generates the more substituted alkene. Since LDA is soluble in our organic solvent THF, pretty strong base again. Notice the temperature change. It's now -78, so there's a cryogen that cools it. LDA goes after the alpha carbon with more hydrogens and therefore generates the less substituted enolate. So that's the kinetic one. So LDA is more about the speed, the rate. What does it see more of? 2 versus 1. It sees the 2. So that generates the least substituted enolate. So from a compound that has 2 different alpha carbons, by choosing the base appropriately, we can select where the reaction is going to happen. Another way that we can control these reactions is by limiting the hydrogens on one of the alpha carbons. So the examples that you see here, the alpha prime carbons have no hydrogens. These are called non-enolizable carbons. So I'm going to highlight those in red here. And when you look at them, you'll see that there's no CHs there. We have 2 examples that are sp3 hybridized carbons and one where it's in a ring. So really what that is doing is forcing the reactivity just to that alpha carbon, which subsequently reduces the number of enolates that can be generated. So if we take this ketone called acetophenone, we treat it with sodium hydride and THF to generate an enolate. The enolate forms. We then quench the enolate with an electrophile ethyl iodide. What's the product that's going to result. So if we expand that out, ethyl iodide, we see the carbon bearing the leaving group, I. That carbon has to become a beta carbon. Then from there, you just throw in the rest of the Greek alphabet. So we need to maintain sort of the carbon backbone from our substrate. So there's one carbon. From that alpha carbon, we're substituting off one hydrogen. Then we're going to make a new carbon alpha to carbon beta bond. So if we look at choice A, there's an alpha carbon. There's beta, but there's no other carbons. So that can't be right because we need two. B is wrong for many reasons, because we have a carbon with too many bonds, and then it's done something where the alpha carbon is non-enolizable. C is not correct because we started at oxidation state 2. We need to remain at 2. This has been reduced. So that's really undergone a nucleophilic addition. So D is correct because we have the alpha, we have beta, and then gamma. So this is the bond that we made. So there's our enolate that results from sodium hydride deprotonating the methyl group. We collapse to form the carbonyl. We react at the alpha carbon. So we attack that. Iodine leaves. So remember, this oxidation state was 1. So it gets reduced down to 0 in the product. So alkylation, when you identify the carbonyl, you identify the alpha, the beta carbon, or carbons. The beta carbons have to be oxidation state 0. That means you've made the bond from an enolate and then some electrophile whose oxidation state was 1 using an SN2 reaction. So given any target molecule, identify sort of the milestones, look at the bond disconnection, and see what it can come from. This can be generalized to anything. Whatever this electrophile is, can be anything over here. You're just making a carbon-carbon bond. So we're going to look at some variants of that, some different named reactions that functionalize the alpha position differently. And then, so that will wrap up alkylation for a couple slides, and then we're going to get into the aldol reaction where the electrophile changes. So we are about out of time here.